Welcome to part 1 of a multi-part video series on solar cell modeling. The goal is to turn a solar cell's datasheet into a working circuit model, and end with a block you can drop into any LTspice sim. The first video is an introduction to the model we'll focus on, the single-diode equivalent circuit, which represents the solar cell with 4 elements. The first of the 4, the current source IPH, that's the photogenerated current due to the photovoltaic effect, where carriers are excited by absorbed light. The diode D represents recombination current, where excess electron-hole pairs recombine inside the cell, returning carriers to lower energy states instead of delivering that energy to the load. The diode itself is described by the saturation current I0 and the ideality factor N. RSH, the shunt resistance, represents the leakage current of the cell. RS represents various resistive losses, including those from internal resistances of semiconductor materials making up the cell, the interconnect, and the contacts. This gives a total of 5 unknowns: IPH, I0, N, RS, and RSH, and together these can closely reproduce a cell's electrical behavior. Solar cell datasheets, though, never give you these directly. What you get instead are the cardinal operating points of the cell. These points are the open circuit voltage, short circuit current, max power voltage, and max power current. Effectively, these 4 parameters define 3 operating conditions on the solar cell's IV curve. Going from left to right on the graph, shorting the output of the cell gives ISC. The output voltage is 0, and the current is the highest that the cell can generate. Next, the knee of the curve is the max or peak power point, the load condition where the cell can generate the most power. Last, if the output of the cell is completely open, the output current is 0, and the voltage generated is the open circuit voltage. The goal of the tool we want to develop is to recover a full model of the cell from just these 4 datasheet points. By the end of the first video, we'll have closed-form solutions for 3 of the 5 model parameters: the photogenerated current, the saturation current, and the ideality factor. Before we get into the math, this is how the code for the project is organized. The extractors, shown in green on the right side of the screen, convert datasheet parameters into usable models. To verify that those extractors work, we'll synthesize cells from randomly generated parameters and use test benches to compare the synthesized cells against extractor results. To build the base of the project, the focus is the single cell at nominal temperature, the cell class, cell extractor, cell synthesizer, and test bench cell that validates them. The thermal and stack level modeling features built up from the single cell approach, so we'll stay at the cell level for a while. We'll start with the extractor itself, then the cell it produces, and finish with the synthesizer and test bench. All of the math builds from one main equation, the one that describes the solar cell circuit itself. So let's go to the circuit and derive it. Current from the IPH source splits into the other 3 branches. Recombination current goes through the diode, leakage current through the leakage resistor, and then the current through the load itself. This is a great circuit to apply KCL, or Kirchhoff's current law. On the right side of the circuit, the load of the solar cell sees load voltage and load current, or VL and IL. This is specifically what's plotted on the right side of the slide. The IV curve is the curve of the solar cell's load. The current through this branch becomes the first term in the equation, IL. To get current through the other branches, we need to define the voltage that the PN junction of the cell sees. We'll define it in terms of the load current and load voltage and call it VD, or the diode voltage. Since load current flows through the series resistor, VD equals the load voltage plus load current times RS. Once VD is defined, the leakage current is straightforward. It's just Ohm's law, VD over RSH. That's the second term of the equation. The next branch is recombination current. In practice, people often describe what this branch represents as power left on the cell. Power the cell could have delivered, but the load condition did not extract. We'll momentarily leave it just as ID and replace it with the Shockley equation in a sec. So that's the third term in the equation. The last branch is the source itself, the photogenerated current IPH. If we stay consistent with KCL, you can see the current direction of the helper arrow and the source are opposite, so IPH in the equation is negative. That gives the 4th term, so now we have a term for each branch of the circuit. And finally, since this is KCL, all branches need to sum to exactly 0 amps. And as promised, the diode current can be defined with the Shockley equation. This is the equation that contains the saturation current I0 and the ideality factor N. VT is the thermal voltage. So rearranging gives the governing solar cell model equation. It uses the 5 model parameters that we're looking to extract from datasheet values: IPH, I0, N, RS, and RSH. You can see that the load current variable shows up inside the exponential, so it can't be isolated with ordinary algebra, which is why we'll lean on some useful numerical methods. And again, it's not just a form of the equation that makes the extraction challenging. Datasheets give us 4 data points, which really just describe 3 operating conditions: short circuit, open circuit, and maximum power. We still need enough constraints to recover the 5 model parameters. Let's start by plugging those operating points into the equation we just derived. For the short circuit operating point, the load is completely shorted out. Voltage across an ideal short is 0, and current rises to the max, which is ISC. Because the current flows through the series resistor, the diode voltage becomes ISC times Rs. Plugging the operating point into the general equation, with the output voltage at 0 volts, the VL term goes away, I load becomes ISC. So that's the solar cell equation at short circuit. For open circuit, it's pretty much the same process. The load voltage becomes the open circuit voltage, and the load current is 0 amps. Since there's no current through Rs, it doesn't drop any voltage, and VD is equal to the open circuit voltage. When load current is 0 amps, the IL times Rs term goes away, and VL becomes just VOC. Since the IL term is also on the right side of the equation here, the whole thing now equals 0. So that's the equation at open circuit. The last operating condition keeps both voltage and load current in the equation, at the point where the cell is delivering the maximum amount of power that it can provide. The diode voltage becomes VMP plus IMP times Rs. So VMP and IMP get substituted in for VL and IL, and nothing in the equation is zeroed out, giving the maximum power condition. So here's the summary of all that. The general equation we derived, and the equations that describe the operating points typically given by datasheets. We'll use the general form and these three equations as the base for solving for all 5 of the model parameters, starting with I0, the saturation current. To get the equation for I0, we start by subtracting the open circuit equation from the short circuit equation. Here they are written out and lined up to subtract. Since they both share the photocurrent term, it cancels out. The -1 terms also cancel out, and you're left with the difference of 2 exponentials and a leakage term. There's a key approximation we have to make here to remove one of the exponential terms. To see it, factor the open circuit voltage exponential out of the terms in the bracket. The term that gets left is very close to 1, which lets us remove it from the equation with minimal impact on solver accuracy. And this resulting equation is a lot cleaner and easier to work with. The single approximation is what makes I0 solvable in closed form, and since this result is reused throughout, it's really the key to the entire extractor. The last step is just to isolate the saturation current I0. We'll use this result multiple times in our extractor's approach, including in the next equation, the photogenerated current IPH. So in addition to the expression we just derived, we'll also use the open circuit equation again. Together, these two expressions isolate the photogenerated current term. Effectively, what we're doing is subtracting the open circuit equation from the result derived for I0. Rearranging the results in the same exact expression on the right side of both equations, so you can either subtract one from the other or set the left sides equal to each other. In the result, it actually helps to keep I0 in the expression. When solving for IPH itself, the I0 term can be dropped since it's many orders of magnitude smaller than the photocurrent, but whenever IPH is used for substitution, leaving I0 in can actually help out. That's exactly what happens in the next equation, the ideality factor n. So for this one, for n, we'll start with the one datasheet operating condition we haven't touched yet, the maximum power point. The goal is to get rid of the I0 and IPH terms in this equation, both of which we now have expressions for. For IPH, we move I0 to the right side and then plug in directly. Keeping I0 in the photogenerated current expression pays off, and it cancels out cleanly. Rearranging what's left gives the diode current at the max power point, and this is an expression we'll reuse in the next video. For now though, we can just get rid of the I0 term by plugging in our expression for it. After some algebra, including combining the product of 2 exponentials, and taking the natural log of both sides, we can isolate n, the ideality factor, into a closed form expression. So that's 3 of the 5 model parameters solved, with closed form expressions for the photogenerated current, saturation current, and the ideality factor. And we also have the diode current expression at the max power point from earlier. So we only have Rs and Rsh left to derive, and that's coming up in the next video. We'll do a 2-dimensional Newton solver to get these 2 last unknowns.